The Limern pumped storage power plant was completed after a decade of planning and construction. A 4 km access tunnel led to the underground caverns, where massive excavation and concreting took place. Equipment was transported via cableways and heavy-duty tunnels. The Mutsi Dam, built in 3 summers, became Europe's highest reservoir dam. By 2015, all major works were finished. In 2016, the reservoir and the plant with 4 250 megawatts pump turbines began phased operation, boosting total capacity to 1,520 megawatts. The construction process of the Obervermundwerk 2 pumped storage power plant saw significant progress in 2017. One of the primary areas of work was the machine cavern, a vast hollow space 800 meters deep inside the mountain. Most of the concrete work in this area had been completed by the end of 2016, with the turbine and pump spirals already partially embedded in concrete. In 2017, the focus shifted to the completion of water jetting tasks. The shield boxes in the underwater section were installed, and the remaining concrete construction for both the machine cavern and the adjacent transformer cavern were finalized. In the 2.8-kilometer-long Silvretta Tunnel, work progressed rapidly, with continuous efforts on the concrete lining. The tunnel excavation had been finished in 2016, and the next step was the installation of the inner shell using prefabricated concrete segments, Tubinger, which were placed on the foundation. The large shell wagon, used as a formwork for the concrete lining, was moved forward in sections, 14 meters at a time. The work in the junction area with the mountain required adjustments to the lining. Each section of lining required approximately 220 cubic meters of concrete, and in total, around 45,000 cubic meters of concrete were used in the tunnel. One of the most complex tasks was the construction of the section where the connection tunnel diverges from the Silvretta Tunnel to the water reservoir. This required extensive reinforcement work to ensure the structural integrity of the system. At the lower end of the pressure shaft, the installation of the distribution pipe, or hose pipe, began in late 2016. This pipe, with 1 inlet and 2 outlets, was designed to transfer water from the pressure shaft to the 2 machine pits. The pipe was assembled from individual parts that were transported to the site and welded together in sections. Workers spent 5 months assembling and welding the pipe, and the final major pipe section was inserted on January 25, 2017. This section was later concealed behind a meter-thick concrete lining, making it invisible in the future, except during internal inspections. Progress was also made on the water reservoir, Wasserschloss, which had been completed in 2016. In 2017, the focus shifted to injecting concrete into both the water reservoir chambers and the reservoir shaft. Small voids between the rock and the concrete lining were filled with grout to enhance the overall stability of the system. This process was crucial to ensure that the structure would withstand the pressures during operation. Steel reinforcements were also installed on-site to further secure the entire system. As construction continued, The fabrication of critical components for the power plant proceeded simultaneously. The manufacturing of these components, including turbines, generators, and transformers, was done at various locations to ensure that they met the required specifications and would be ready for installation once the structural work was completed. Each component was meticulously tested for accuracy and quality, ensuring that they would withstand the high forces and operational stresses expected during the plant's operation. The construction of the Yusufeli Dam involves massive concrete placement and precise engineering. As of now, 3.765 million cubic meters of concrete have been poured to reach a body height of 250 meters. The process includes continuous concrete pouring in layers, with work progressing rapidly around the clock. Upon completion, the dam body will reach 275 meters, making it Turkey's tallest dam. Each stage of construction is carefully monitored to ensure structural integrity and alignment with design specifications. The cable-stayed roof was first assembled on the ground by connecting the steel structure and installing stay cables. Once fully prepared, Freycinet's team used a synchronized lifting system to raise the entire roof structure. The lift was carried out gradually and precisely, aligning the roof with its final position atop the stadium. This process was completed in July. The installation of the Bibo precast concrete arch is a carefully coordinated process that ensures structural integrity and precision. The process begins with the transportation of precast concrete arches to the project site, followed by positioning using a hydraulic hoist. The hydraulic hoist lifts and aligns the heavy double-cell C42T arches in place with precision. Each arch is carefully secured to ensure stability and longevity. The Bibo system's design allows for quick installation while maintaining exceptional strength and durability, making it ideal for infrastructure projects like bridges and tunnels. The final result is a robust and reliable structure that meets all engineering requirements. This method not only enhances construction efficiency, but also ensures long-term sustainability of the built environment. The production of high-voltage concrete signal towers for railway autoblock systems is a precise process. Each tower begins with the careful mixing of concrete, followed by molding in custom-designed forms. The production line ensures exact specifications for strength and durability, meeting the stringent technical requirements for railway safety. Once formed, the towers undergo rigorous testing before being delivered to the railroads, ensuring they can withstand harsh environmental conditions. Bridge construction is a complex, multi-phase process that requires meticulous planning, engineering expertise, and careful execution. It begins with a comprehensive site survey to assess the geological conditions, water flow, soil stability, and topography. These findings guide engineers in selecting the most appropriate bridge design, materials, and construction techniques. Once the engineering and environmental assessments are complete, the design phase begins. Engineers create detailed plans for the substructure, foundations, abutments, and piers, and superstructure, beams, slabs, expansion joints, including drainage, traffic barriers, and lighting. The necessary permits and environmental approvals are obtained during this phase. Construction begins with site preparation, which includes clearing vegetation, redirecting traffic, and installing temporary access roads and safety barriers. Next comes excavation, along with the installation of deep foundations such as driven piles or bored piles, depending on the soil conditions. These foundations carry the vertical loads and transfer them to deeper, more stable soil layers. Next, the construction of reinforced concrete piers and abutments will support the bridge's superstructure. With the substructure complete, attention turns to the superstructure. Girders made of steel or pre-stressed concrete are lifted into place by crane. In some cases, segmental or stepped structures are used for longer spans. Floor slabs are cast in place or installed as precast units, which are then cured and surface treated. The bridge deck is then paved with asphalt or concrete, depending on traffic loads and environmental conditions. Safety features such as guardrails, pedestrian walkways, if applicable, and expansion joints are added, along with drainage and lighting systems. The transition between the bridge and the connecting roads is carefully graded and compacted to ensure smooth traffic flow. Erosion control measures and landscaping are also implemented around the bridge construction site. Throughout all stages, strict quality control is implemented, with engineers checking materials, dimensions, and structural integrity to ensure the bridge meets design specifications and safety standards. Before the bridge is open to the public, it will undergo load testing to simulate real traffic conditions and verify the bridge's performance. After successful testing and certification, the bridge is put into operation and officially opened. This process ensures the construction of a safe, sustainable, and efficient bridge that meets transportation needs while minimizing environmental and economic impacts. Concrete is poured carefully into the formwork, vibrated to eliminate air pockets, and leveled using tools under expert supervision to ensure proper compaction and surface finish. The application of AAC blocks in house construction. First, the foundation surface is cleaned and leveled. AAC block adhesive is prepared by mixing with water and applied as a thin 3 to 4 millimeters layer using a notched trowel. The first row of AAC blocks is carefully aligned and tapped into position with a rubber mallet. Each subsequent row is placed with staggered joints for stability, with adhesive applied to both horizontal and vertical surfaces. The blocks are lightweight and easy to handle, allowing for faster wall assembly. Openings for doors and windows are incorporated as per the design. Blocks can be trimmed with simple tools to fit around corners or fixtures. No curing is needed, which saves water and labor time. Once walls are completed, electrical and plumbing chases are cut directly into the block surface. Finally, external and internal finishes like plaster or paint are applied to complete the structure. Raw wood waste, mainly sawdust and shavings, is first separated and ground into fine fibers using a hammer mill. The material is then dried to 6 to 9% moisture using a biomass burner fueled by production fines. Next, the dry fiber is compressed under high pressure in a pellet mill to form wood pellets. These pellets are cooled, screened, and packaged or loaded in bulk for shipping. The E50 concrete pipe production process using the CGM vibrating demolding machine begins with dry cast concrete loaded into the mold. High-frequency vibration compacts the mix within the form. Once properly consolidated, the mold rotates 180 degrees to demold the product directly on the floor. The machine's mobile egg layer design enables continuous production with minimal labor. The production process of the Aufbau DMU 600G at Schneider form involves precise assembly of the machine base, installation of linear guideways, mounting of the column and spindle unit, and integration of electrical components. Final steps include system calibration, software configuration, and comprehensive testing to ensure operational accuracy and performance. The hydraulic cold billet shear manufacturing process involves precision cutting of billets, with models designed for sizes up to 180 by 180 millimeters. After raw materials are prepared, the billets are securely fed into the shear machine. Using hydraulic pressure, the machine cuts the billets efficiently, ensuring smooth, clean edges. The production process includes rigorous testing and quality control to meet international standards. This shear machine is widely exported to various countries, supporting industries that require robust and reliable cutting equipment. The Okuma 5-axis lathe, model Multis U4000, is renowned for its high-performance capabilities in gear milling, particularly for machining complex gear shafts. This versatile machine is designed to handle multiple operations, providing precise and efficient machining in a single setup. In gear milling, the Multis U4000 excels with infomilling, a cutting-edge technology that enables high-efficiency, accurate gear production. For instance, at B0 degrees, it processes gears with a module of 8 and a size of 140 by 80. The machine also supports milling at various angles, such as B15 degrees from Module 4 gears and B12 degrees from Module 8, making it adaptable to different gear specifications. With the ability to mill herringbone pitch gears, the Multis U4000 can work on larger sizes, like 140 by 80, achieving precise cuts at different module settings, such as Module 4 or 8. This machine is ideal for producing gears with complex geometries, offering high flexibility and precision for a wide range of gear machining tasks. The Multis U4000 combines robust functionality with high-speed cutting, ensuring efficient production of high-quality gear shafts for industries requiring detailed and durable components. Daiko, Daiwan Applied Engineering, is a leading Korean company specializing in the design and manufacture of advanced industrial equipment, especially in the production of various springs and other precision components. The company provides a wide range of high-quality machinery that is essential in industries such as automobile, electronics, and machinery manufacturing. Daiko's coil spring manufacturing machines are designed to produce high-performance coil springs used in automotive suspension systems and other mechanical applications. The machines are capable of precisely controlling spring diameter, pitch, and other important parameters, ensuring consistency and durability. The company's stabilizer bar manufacturing machines are used to produce stabilizer bars, which play a vital role in improving vehicle handling and reducing body roll. These machines ensure that stabilizer bars are manufactured to exact specifications, providing optimal performance in automotive applications. In addition, leaf spring manufacturing machines are widely used to produce leaf springs, which are an integral part of the suspension system on heavy vehicles such as trucks and buses. The machine ensures high precision and durability, meeting the needs of heavy-duty applications. For industries that require high quality and precise springs, precision spring manufacturing machines provide unparalleled precision in the production of small springs for a variety of uses. Dayco also offers a range of material handling machines and testing machines to ensure the quality and performance of components throughout the manufacturing process. These machines allow for efficient processing and rigorous testing, ensuring that products meet the highest standards of reliability and performance. The solid-cam aluminum rim utilizes advanced iMachining 3D technology to achieve precision machining with significant time savings. The process begins by setting up the aluminum rim on the CNC machine, where iMachining 3D optimizes the tool paths to maximize efficiency. With its advanced algorithms, it reduces machining time by up to 70%, sometimes even 90%. The machine operates smoothly, ensuring high-quality results while minimizing waste. After the machining process, the rim is carefully inspected for accuracy and quality, ensuring it meets the required standards for further use or shipment. The TESIS production process begins with in-house design and 3D modeling, utilizing advanced software for precision. Raw materials are processed using CNC machines to achieve exact specifications. Parts are tested for conformance before undergoing heat treatment, branding, and paint coating. Functionality checks are rigorous. Each pistol is fired, and its barrel, slide, and safety system are thoroughly tested for compatibility. Pistols are also performance tested under varying conditions, including temperature extremes from -33 degrees Celsius to +55 degrees Celsius and underwater. Following final inspection, cleaning, lubrication, and packaging, the pistols are shipped globally, including to the US and over 30 countries. Inside this facility, glass-lined steel equipment takes form through a blend of mechanical fabrication and chemical expertise. Production starts with carbon steel vessels, shaped through precision welding and machining. These forms are then coated with a specially formulated glass enamel. After applying the enamel, each unit enters a high-temperature kiln, where it fuses with the metal at temperatures over 800 degrees Celsius. This creates a corrosion-resistant, chemically inert surface. Each firing cycle is monitored closely to ensure uniform bonding between glass and steel, preventing future delamination. Post-firing, technicians inspect the lining for consistency, smoothness, and any surface flaws. Reactors, distillation columns, and storage tanks are then assembled with fittings and accessories tailored for industrial chemical use. The final inspection ensures structural integrity and compliance with safety standards before the equipment is shipped to industries like pharmaceuticals, chemicals, and dyes. High-precision shaft turning takes center stage at this facility. The Hankook propulsion shaft lathe processes massive shafts used in marine and heavy industries. Raw steel shafts are mounted and aligned for balance before machining begins. Using multiple cutting tools, the lathe gradually reduces the diameter to required specifications. During operation, constant monitoring ensures tight tolerances are met. Surface finishing and threading may follow, depending on application needs. This process delivers shafts capable of withstanding immense rotational forces under demanding real-world conditions. The Ermuksen Speed Bend Press Brake bends mild steel up to 45 mm thick with precision. This advanced machine ensures flawless 3,100 mm by 800 mm bends, vital for custom fabrication. In the world of high-performance engines, precision is key. The LKW 6-cylinder crankshaft is crafted using advanced inner milling techniques, ensuring top-tier quality. The process starts with rough machining, where the base structure is thoroughly shaped. This flexible manufacturing system by Heller efficiently produces both crankshafts and camshafts, using state-of-the-art equipment and automation. Each component is carefully processed to meet the highest automotive standards, ensuring optimal engine performance and durability. The result is a highly reliable crankshaft built to withstand the toughest driving conditions. The fully automated pump manufacturing plant in China showcases cutting-edge technology and precision in every step of production. The process begins with the impeller housing being shaped through an automatic stamping line, followed by a progressive die stamping line for intricate component details. Robots are used in the stamping of impeller inner braces, ensuring efficiency and accuracy. The impeller diffusers are then welded automatically in a dedicated welding line, guaranteeing strong, reliable connections. The next stages involve welding workstations, where components are meticulously assembled and tested. Finally, the pumps are carefully packaged, ready for distribution. This fully automated system ensures high-quality products and streamlined production processes. Through its advanced automation, the plant minimizes human error and enhances productivity. Every pump is rigorously tested to meet industry standards, ensuring long-lasting performance and reliability. Get a close-up look at the advanced manufacturing process at Sany's Super Drilling Machinery Factory. The process begins with precision machining of key components, followed by assembly using state-of-the-art equipment. Automated systems streamline operations, ensuring efficiency and consistency. Each machine is thoroughly tested for quality before it moves to the final packaging stage, ready for delivery to customers around the world. Steel tubes are cambered, cut, and welded into shape. Structures undergo in-process inspections, then full-scale testing with loads applied at multiple points. After testing, surfaces are prepared and finished in climate-controlled facilities. Components are then galvanized using a 65-foot kettle. Final inspections are performed before shipping. Discover the precision involved in assembling the LK16 Zagier's Ozorkow Optum plate structure. Made from S235 steel with 6 mm thickness, the structure is mounted using Class 8.8 bolts, ensuring durability. After assembly, it is carefully placed on a track for insertion into the target location. The production of steel scuba cylinders begins with chromoly alloy blanks lubricated using zinc phosphate and sodium stearate. These blanks undergo 2 to 3 deep-drawn ironing operations using high-tonnage presses, reducing the diameter and thickness while ensuring uniform wall thickness. After trimming the open end, the shell is heated to about 1,600 degrees Fahrenheit for hot spinning, which forms the shoulder and neck using CNC-controlled tools at 1,000 RPM. The cylinders are sealed and heat-treated in computer-controlled furnaces to ensure consistent mechanical properties. After quenching and tempering, internal threads and O-ring grooves are machined with synthetic coolant to avoid hydrocarbon contamination. Shot blasting removes oxides from the inner and outer surfaces. Each cylinder undergoes hydrostatic testing by volumetric expansion. Internal volume and tear weight are recorded, and the cylinders are pressurized to verify integrity. Afterward, they are cleaned, dried, and permanently marked with specifications and serial numbers. Finally, scuba cylinders are hot-dip galvanized by immersion in molten zinc for maximum corrosion resistance, then cleaned, polished, and packaged for shipment. The Trubin Series 7000 is a high-speed, ergonomic die-bending machine. It uses a press beam to push sheet metal into a V-shaped die, creating precise bends. With intelligent software, back gauges, and automation, it ensures accurate positioning, operator comfort, and high-quality production of both simple and complex parts. The manufacturing process at PFI Tiramala begins with the use of direct reduced iron ore as the raw material, which is charged into a 30 metric ton mega furnace. The furnace uses giant electromagnets to melt the DRI, achieving a temperature of approximately 1,650 degrees Celsius. The molten metal is then extracted and transferred to a crucible, where it is purged with nitrogen to ensure homogeneity and uniform temperature. Once the metal reaches a consistent state, it is moved to the continuous casting machine. The molten metal flows from the ladle to a tundish and then to a mold where the casting process begins. The extruded solidified metal billets are cooled in primary and secondary mist-type cooling chambers, maintaining the shape, integrity, and quality of the billets. Next, the billets are transferred directly to the rolling mill without delay. In the rolling mill, the billets undergo gradual size reduction. The material passes through a roughing mill, followed by intermediate and finishing mills. This ensures the desired fine-grained structure of the rebar. Advanced rolling technology, including a loop scanner and tensionless rolling system, ensures that the bars achieve a perfectly round shape. After the final rolling process, the bars are quenched to enhance their tensile strength, followed by atmospheric tempering at the cooling bed. This ensures the bars have a soft core for flexibility and a hardened surface for strength and grip. making them corrosion and stress resistant. Finally, the rebar is cut into specific lengths, packaged into bundles, and stored. The production of standing lock seam elbows and reducers using the Spiro Gorlocker Combi T involves two main workstations, a flanging station and a seam closing station. First, the sheet metal segments are flanged to prepare the edges. Then, the parts are transferred to the seam closing station, where the standing lock seam is formed. This design minimizes welding to a single longitudinal seam, ensuring high rigidity. The dual station setup enables continuous operation without tool changes, supporting fast. The CNC lathe is hand-programmed to machine a part from 12L14 steel, using a constant surface speed, CSS, of 800. The roughing pass cuts at a depth of 0.030 inches and a feed rate of 0.025 inches per revolution. The process starts with defining the stock and setting the 0 point. G-code is manually written, beginning with a safety line and tool selection. A roughing cycle is programmed to use straight and contouring motions. The operator calculates spindle speed and feed manually based on the diameter. The part is shaped step by step, with each move precisely coded, including tool retracts and final finishing passes. The code ends with tool retraction and spindle stop, completing the machining cycle. The new production line at Irazar Forge starts with open die forging, which forms flexible pre-shapes from raw metal. These are then refined through closed die forging, using interchangeable dies to shape the product and reduce material waste. During forging, high-pressure water removes surface impurities from the hot metal. After this, each piece is ground by hand to remove defects before heat treatment. The parts are then heated and cooled, using air, water, oil, or polymer to improve strength, elasticity, and durability. Following heat treatment, the surface is cleaned by shot blasting to remove scale. Next is machining, where the part or the machine moves depending on product size. Finally, components are assembled, combining welded structures, seals, and hardware. The finished products, including crane hooks and sheaves, undergo non-destructive testing and proof load testing to ensure reliability in demanding industrial applications. The JCO press bending line 41114 is designed for the efficient forming of large diameter steel pipes. The process begins with a flat steel plate that is precisely positioned and clamped on the press bed. The machine then performs sequential forming in 3 stages: J forming, C forming, and O forming. In the J forming phase, the press bends one side of the plate, creating the first curve. Next, during C forming, the opposite side is bent to form a symmetrical C shape. Finally, in the O forming step, the central press section closes the plate into a complete circular pipe shape. Throughout the process, hydraulic rams and automated positioning systems ensure consistent accuracy and repeatability. Once the O form is completed, the pipe is unclamped and transferred for further processing, such as welding, expanding, or ultrasonic testing. This JCO forming technique allows for minimal material stress and high dimensional precision, making it ideal for producing pipes used in oil, gas, and water transmission industries. Walls & Earl manufactures high-tech cast products for demanding industries such as food, plastics, paper, and steel. In 12 halls with over 80 CNC machines, processes like turning, milling, and grinding are precisely carried out. The foundry features 8 induction furnaces producing castings up to 130 tons. Specialized departments handle thermal rollers with hot grinding and balancing. Quality is ensured through continuous metallurgical testing, while the design department supports custom solutions and product innovations tailored to customer needs. The Trump TrueBend Series 5000 is one of the most versatile and productive press brakes available for precision metal bending. It is engineered for high-speed, high-accuracy bending operations, making it a preferred solution in advanced fabrication environments. This machine features a powerful on-demand servo drive which operates quietly and saves energy by only running when needed, significantly boosting overall efficiency. Its 6-axis backgauge system enables complex bending operations with perfect part positioning, while the ACB, automatically controlled bending, systems available in both wireless and laser versions, ensure outstanding angle precision right from the first bend. This eliminates the need for manual rework and reduces material waste. The TrueBend 5000 also includes the Toolmaster Automatic Tool Changer, which greatly shortens setup times by automatically switching tools in seconds. Operators benefit from an intuitive touchpoint TrueBend control system that resembles tablet navigation, making setup and operation extremely user-friendly. Designed with ergonomics in mind, it includes height-adjustable footrests, the Magic Shoe foot control, and support brackets that can be tailored to each operator's comfort. With press forces ranging from 850 to 3,200 kilonewtons and bending lengths up to 4,420 millimeters, the TrueBend 5000 can handle a wide range of tasks, from small batches to large-scale production. Rottler Maschinenbau has completely overhauled the vertical lathe Untitled, restoring it to a high-performance, future-ready condition. The refurbishment included installing a new Hydroelectric 426cb contouring control system, along with updated drive and measuring systems. This advanced controller ensures precise and flexible operation, meeting the demands of modern machining processes. In addition, Rottler redesigned the machine's safety concept to align with both current and upcoming safety standards. These upgrades not only restore the machine's functionality, but also significantly improve its efficiency, reliability, and compliance. With the mechanical structure renewed and the latest control technology implemented, the Untitled vertical lathe is once again ready for demanding industrial applications. The CNCC SK 8011 high-speed gantry wheel lathe is a precision machine designed for machining wheel sets of medium and high-speed electric multiple-unit trains. It performs multiple operations including turning the wheel rim, shaping the flange profile, machining the inner and outer wheel faces, and processing the brake disc located between the wheels. The machine is equipped with a dual-side clamping system and full-dimension measurement functions to ensure high accuracy and consistency. The CSK 8011 is suitable for both new production and overhaul processes. It ensures critical technical requirements are met, such as maintaining wheel set geometry, internal spacing, alignment, wheel diameter difference, and brake disc surface quality. By supporting real-time measurement and correction during machining, the lathe improves operational safety and extends the service life of the wheel sets. With its high-speed performance, robust structure, and automation capabilities, the CSK 8011 is a key solution in modern railway maintenance and manufacturing facilities, ensuring the precise and efficient processing of train wheel components while meeting strict industry standards. The DMG Mori NTX 2500 is a high-precision, high-performance turning and milling center designed for complex machining tasks, including the production of surgical hammers. Equipped with a compact, shortest spindle in its class measuring 350 millimeters, it delivers 122 Newton-meters of torque, enabling complete machining of 6 faces in a single setup. The machine supports simultaneous 5-axis machining via a direct drive motor on the B-axis, increasing flexibility and precision. With a maximum workpiece diameter of 670 millimeters and a length of up to 3,135 millimeters, the NTX 2500 can accommodate a wide range of components. The X-axis travel of 675 millimeters, the Y-axis travel of 300 millimeters, and the Z-axis travel of 3,062 millimeters provide a spacious machining area. The machine's design includes a dual spindle and an automatic tool changer, which reduces setup times and minimizes errors from multiple setups. The NTX 2500 incorporates Silos, an app-based control system that provides intuitive operation and seamless integration into the digital manufacturing environment. This system allows for real-time monitoring and efficient management of production processes. Machine thermal stability is maintained through coolant circulation in the spindle, motor, and ball screw, ensuring high-precision machining. Ingersoll, a member of the IMC Group, precision cutting tools for advanced machining. Discover performance-boosting solutions at Ingersoll Cutting Tools. The Georg Slitting Line 1800 is a high-performance longitudinal cutting system designed for maximum efficiency and precision. It ensures high output and material flow through reduced tooling times and elevated production speeds. The machine guarantees excellent cutting accuracy thanks to high-precision knife shaft bearings, delivering burr-free cuts with minimal shaft deflection even during high-volume operations. A movable braking unit allows for precise winding, adapting to increasing coil diameters, and enabling operation without a separating system at the coiler. This slitting line also offers exceptionally gentle handling of sensitive materials, such as automotive surfaces, coated strips, or annealed stainless steel, through surface-adapted braking techniques. It features energy-efficient regenerative systems and specially rated drives to minimize power consumption. Built for strength and durability, the line processes materials with tensile strengths exceeding 1,400 N per square millimeter and yield points up to 1,000 N per square millimeter, making it ideal for demanding industrial applications. Katahdin Cedar Log Homes processes logs by drying them, shaping them in a planer mill, and then using a computerized house line for precise cuts, drilling, and labeling. This ensures easy assembly. Bare core panel production process at PT Phoenix Agung Pratama. The production of bare core panels at PT Phoenix Agung Pratama begins with carefully selected Albazia falcata wood, known for its lightweight properties and fast growth, making it highly suitable for engineered wood panels. The raw logs are initially sawn into small rectangular blocks, which are then kiln-dried until the moisture content is reduced to a maximum of 12%. This step is essential to enhance dimensional stability and ensure a strong adhesive bond. After drying, the blocks are processed into narrow strips. These strips are lined edge to edge and glued using polyvinyl acetate adhesive, which is widely used for its environmental friendliness and strong bonding characteristics. The glued strips are arranged in a continuous layer, forming the core structure of the panel. The glued assembly is then sent through a hot press, where high pressure and temperature are applied to bond the strips firmly together, creating a solid and uniform core. Once pressed, the panels are cooled and precisely trimmed to reach the standard size of 13.2 mm thickness, 2,480 mm length, and 1,260 mm width. The final panels are inspected for quality, including strength, surface smoothness, and dimensional accuracy. They are then stacked and prepared for lamination or shipment. Bare core panels are commonly used in door manufacturing, furniture components, and other wood-based constructions due to their strength-to-weight ratio and consistent quality. The veneer slicer BB1130 offers a precise and efficient method for slicing veneer sheets, ideal for industries requiring high-quality wood processing. The process begins by feeding logs into the slicer, where they are carefully aligned and cut into thin, uniform layers. The machine operates with advanced technology to ensure consistent thickness, maximizing yield, and minimizing waste. Each veneer slice is then inspected for quality before moving on to the next stage, whether for further processing or preparation for shipment. This high-performance equipment improves productivity and guarantees top-tier results. With its robust design, the BB1130 can handle a wide variety of wood types, offering versatility in operations. The system's automation ensures a smooth and continuous process, reducing the need for manual intervention. Furthermore, the machine's energy-efficient design contributes to lowering operating costs while maintaining high output. The advanced safety features provide a secure working environment, ensuring smooth operations without compromising worker safety. Additionally, the machine's durable construction reduces the frequency of maintenance, ensuring long-term reliability. The user-friendly interface also makes it easy for operators to monitor and adjust settings for optimal performance. The DSC 3259 is a handheld wood-cutting tool designed for precision and efficiency. The process begins by securely holding the tool and guiding it along the wood surface to make clean cuts. The powerful motor ensures smooth cutting through various wood types while maintaining accuracy. Its ergonomic design allows for comfortable use during extended operations. After each cut, the wood is inspected for quality, ensuring high standards are met before moving on to the next step. The DSC 3259 enhances workflow by providing easy handling and consistent results. Additionally, its compact design makes it ideal for tight spaces and intricate The oriented strand board production process at Georgia Pacific begins with harvesting logs, typically from pine trees. These logs are fed into stranders, which cut them into long, thin wood strands. The strands are then dried in industrial dryers to remove excess moisture. Throughout the process, monitoring systems ensure quality control and consistency. Once dried, the strands are blended with resin and wax, then oriented in layers, pressed under high heat and pressure, and trimmed to standard sizes. This completes the OSB production process, resulting in durable, engineered wood panels for construction use. This state-of-the-art Weinmann closed panel timber frame manufacturing line enables efficient production of closed panel timber frames using modern construction methods. The line includes advanced technology for precision cutting and assembly, optimizing the manufacturing process for both quality and speed. Supervised viewings are available by appointment, ensuring a thorough inspection of the equipment. Offers for the plant, including the Dodd Engineering floor cassette line, will be considered in writing, with details on removal and dismantling provided. This is an opportunity to acquire cutting-edge manufacturing equipment in the timber frame industry. The log home assembly process at Discovery Dream Homes begins with the precise preparation of the subfloor, ensuring accurate measurements. Logs are carefully numbered and arranged according to blueprint specifications. The first course of logs is secured to the foundation using anchor bolts, with subsequent courses interlocking through timberlock joints. Foam gaskets and caulking are used to create airtight and watertight seals between each log course. As the structure rises, logs are securely fastened with pre-drilled holes for electrical and plumbing. The team ensures that each component is precisely positioned, making the assembly process efficient and smooth. Finally, through bolts and optional compression springs are added to provide long-term stability and support, ensuring a durable and energy-efficient home. The attention to detail and quality craftsmanship throughout the process guarantees a reliable and lasting structure. Sugar Australia is the nation's leading producer of refined sugar. The refinery processes over 300,000 tons of white sugar annually. The refining process begins with washing the raw sugar, separating impurities through centrifugation, and clarifying the wort through phosphating. Activated carbon removes color, followed by evaporation and crystallization. The sugar is dried, processed, and transported to McKay Harbor for packaging and distribution. High-speed automation slices rows of ice cream bars, each already embedded with a wooden stick. These preformed treats are precisely cut, then guided into synchronized chutes that position them for individual wrapping. The machine's flow ensures seamless transition from frozen slab to neatly packed, ready-for-market ice cream sticks. The handle robot is designed for logistics, autonomously performing tasks like pallet building and depalletizing. It uses an onboard vision system to navigate and locate boxes for placement. Force control ensures that each box is securely placed against its neighbors. Capable of handling boxes up to 15 kilograms, handle works with pallets up to 1.7 meters tall. Crafting baccarat crystal is a symphony of heat, precision, and tradition. The process begins with silica sand, potash, and lead oxide, ingredients melted in a furnace reaching over 1,400 degrees Celsius. Once molten, the glowing crystal is gathered on blowpipes by artisans, and mouth-blown into rough forms. These initial shapes are then placed into molds for refined shaping. Each mold is carefully designed to guide the crystal into its final form, ensuring symmetry and consistency. After molding, the crystal is reheated to maintain its malleability before shaping continues. To prevent deformities, the timing and temperature of reheating are closely controlled. This ensures that every piece retains the correct thickness and structure throughout the process. A supervisor monitors each stage to guarantee consistency across all items. Artisans work in teams, with each specialist performing a distinct role, from blowing and molding to trimming and reheating. The partially formed pieces then undergo annealing, a cooling process lasting several hours that prevents internal stress and cracking. Once cooled, the crystal is meticulously cut and polished. Using diamond-tipped wheels, craftsmen carve facets and decorative patterns into the surface. Each cut requires steady hands and years of experience, as even the slightest error can ruin a piece. After cutting, the crystal is polished with fine sand and felt wheels, restoring its natural brilliance. Some pieces are further enhanced with engraving or gilding, adding layers of visual depth and artistic flair. The final step is a rigorous quality check. Each item is inspected for clarity, symmetry, and craftsmanship. Only those meeting Baccarat's high standards are approved. This blend of tradition and technique defines Baccarat's legacy. With centuries of refinement behind every piece, the crystal captures both artistry and heritage in a single gleaming form. In Sri Lanka, the journey to discover gemstones is an exciting and hands-on adventure. At Ratnapura, we explore the depths of sapphire mines, 50 feet underground, where miners dig through mud and sand to uncover valuable stones. The rough stones are then washed in rivers to reveal hidden gems. After extraction, the stones are meticulously cut and polished. From the bustling gem markets to the cutting workshops, the entire process is an impressive display of skill and tradition.